The computational fluid dynamic world has an almost infinite number of models to compute the Navier-Stokes equations for fluids. Problem spaces that arise from simulating the aerodynamics of a vehicle with a low Mach number reduces the options considerably. This is because the parameters that influence the solution are reduced. Other fluid problems have different parameters and their models are accurate for those, such that there is basically a computational model for almost any problem, and if not, there's probably a PhD candidate that is working on that, and similarly in industry. The go-to method for vehicle aerodynamics is the Reynolds averaging RANS with the K-omega SST turbulence model, using the simple algorithm. It is a solid way to get reasonable results with well-known and understandable limitations. The steady-state output gives very helpful suggestions, but is postdictive, requiring validation. Great for building general trends. One other ways to look at the flow over a body problem is through transient simulations. RANS gives you an indication of where the flow eddies are. Large eddy simulations, LES, is much more explicit. The difference is fundamental. I'm going to go through with as much detail as necessary to give you an understanding why one is useful or not. This is going to get a bit technical, but I don't think there's a decent source related to the usability of the LES process. There is plenty of sources devoted to the underlying theory and the CFD setup process, but not much for interpretation. Firstly, the basics. For the finite volume method, where the problem space is divided up into an unstructured grid or mesh, each of the cells will have a calculation performed on them relative to the neighbouring cell. There's a whole massive subject just in this process that we will be skipping. But for the Reynolds averaging, RANS, it is implemented by the simple algorithm. For transient LES calculations, the piezo algorithm is used here. Others are available. Step 2 is almost all the difference between the algorithms. The outcome is Reynolds averaging over time, and transience is time dependent, subject to the size of the time step. This is almost enough information to get you going. I'm going to dig into what this means for transient simulations. With the fundamental difference is, RANS is time averaging. By definition, the fluctuations in the flow are smoothed, making it more difficult to see oscillatory behavior. Any oscillations are inferred rather than perceived. LES intends to solve the eddies directly, or 80% of them with each time step. RANS models the whole fluid domain through each iteration. It tends to give a better result with coarser meshes. Over a body that isn't dominated by turbulent flow, it gives quite good results. Better meshes give better results, of course, but the constraints aren't time dependent. Which brings us to the last big difference, computational cost. Calculating each time step, with those being at least 10 to the negative 4 seconds, relatively small mesh counts can take 16 cores 24 hours for 1 second of flow. At 20 meters per second, a second is 20 meters. Each time step is 2 millimeters. Now, you may not need to record each time step, as the whole domain takes 10 gigabytes of storage for each time step. So maybe every 10 centimeters is good enough. Recording a whole second is still beyond reasonable. Capturing 0.1 seconds is 200 gig of storage, which means that the frequency of oscillations can't be much bigger than this. They can be bigger because you can see them recorded in the wake. We are starting to see the transient flow is important for capturing formation of eddies, which happens whenever energy is placed into a fluid through pressure gradients and shear stress. In our case, it can also come from anything such as convection. Now, the difference in length scale between the eddies created by the pressure gradients and shear stress is almost infinite. This is actually most of the problem in fluid simulations, the length scale. the length scale that is most difficult to capture is the one in the viscous range. The good thing is, most of the energy that is within the eddies is in the largest 80 to 90%, leaving the most difficult to capture eddies in the viscous range containing the minimal energy, so modelling this region will be of least consequences. That's not to say it's irrelevant, but basic models can give usable results. The theory behind this was built up in the first half of last century with significant contributions from Kolmogorov and the universal equilibrium theory. I'll briefly touch on this important subject, but it is a really big area. This plot is the most important and representative for turbulent modelling, plotting the energy distribution on the length scale. Y-axis is the energy scale, with the x being the inverse length scale, presented as the wave number. Shown like this, such that the large eddies are on the left and the viscous range is on the right. Using a log-log plot for the energy cascade illustrates that the large eddies, commonly referred to as vorticities, last a long time and lose energy the slowest. At the other end, the energy is much reduced, and therefore the turbulence at a small scale has very little energy, diffusing it into heat at a molecular scale relatively quickly. Anyway, this small scale is where all the modelling takes place, with the boundary layer conditions considered here as well. For steady-state simulations, there is an important measure for the accuracy known as Y+, which is referring to this plot. If you test a case for this parameter and you have a value of less than 1, then the mesh is modelling all of the domain outside this part of the plot. It also means that the case is likely more accurate than otherwise. Then conversely, if your case returns a value above 30 and between 300, then the turbulence model is capturing the flow in the whole plot, which is fine, but adverse pressure gradients at the extents of the simulation are much less accurate. In all of this, I'm assuming that there's a reasonable gradient of mesh sizes across the whole domain. Fitting the mesh to the model is usually the most difficult, especially when getting to the length scale needed to achieve a Y+ of 1. Assessing whether a transient simulation has an accurate mesh is a little different. As mentioned, we want to capture most of the energy in the fluid that stands for between 80 and 90%. So we're going to have to measure the total kinetic energy of the flow. That is 80 to 90% captured by the mesh and the rest modelled by the turbulence model. This begs the question, how does the mesh capture eddies? In an unstructured finite volume method, the mesh is just a mass of cells adjoining each other with their faces. Fluid flows or is simulated to flow through the faces of the cells to their neighbours. Eddies are three-dimensional, but it is difficult to visualize how they sit in the mesh. Reducing it to 2 dimensions, we have a grid. An eddy over the grid will capture the fluid passing through the faces of each cell. Changing the eddy size to the number of cell ratio gives us the lowest number of cells an eddy can be captured, which in theory is 4. The actual number is higher, but 4 is the absolute limit. When the LES algorithm is filtering the wave number, this forms the lowest length scale. From this length scale, the turbulent model is implemented, removing the eddy from the mesh and placing it into the model as the energy cascade determines. Not removing the eddy from the mesh means the viscosity of the physics hasn't been implemented. Conversely, growth of the boundary layer would never enter the mesh. It is with the turbulence modelling that both production and dissipation are implemented. Running an LES simulation, the length scales are filtered to implement the turbulence model for the mesh when the eddies are too small and not captured. Measuring this is done by calculating the total turbulent kinetic energy within the flow, which is the sum of the energy resolved by the mesh and the subgrid calculated by the turbulent model. For this particular case, the turbulent fields need to be calculated, as well as the Reynolds stress tensor, for the turbulence resolved by the mesh and the subgrid scale of turbulence. Implemented in OpenFOAM, for checking the accuracy of the simulation, I would create an ISO volume for the 10 to 20% of the unresolved turbulent kinetic energy. The mesh is almost 17 million cells. It's limited to 15 million before the inflation layer, so we get this weird gap, which is a problem. Placing the ISO volume for the 0 to 20% grid scale calculation, I get this. So there's still a bit of work. At 0.4 milliseconds, when I started to record the case every 100 milliseconds, still hadn't fully developed. To get to 0.6 seconds, 24 hours. This was just an exercise in setting up the case to do further development of a vehicle. The fact that there is still work is okay. However, it is a good illustration of how computationally expensive transient simulations are. I will not be getting a fully resolved case, but I'll be able to map the results. I'm close enough to get useful results for future cases. The gap in the mesh is an interesting visualization of how the turbulence model kicks in for the lower quality mesh, but then adds eddies back into the mesh where the mesh is better. Not all the information is put back into the flow, but I thought it was an interesting mistake. Anyway, here's some results from this case to give an illustration what we will be able to see. The slice through the middle is a representation of the body's characteristic flow. The wake is clearly defined, pulling energy out of the virtual wind tunnel or putting energy in for the moving body for something out in the wild. Looking back behind the body with the subgrid turbulence energy, there is a hint of the vorticities projecting off the sloped back. The Q criteria is a go-to ISO volume visualization technique for transients. Seeing the eddies visualized like this shows the length scales, the large eddies or the vorticity carrying the most amount of energy, and we can see these really well. Turbulence is made up of a large number of low energy eddies, and that is clear with the pocket directly behind the rear. The velocity magnitude color map on the ISO volumes reinforces the different energies. Total pressure and the velocity across the slice makes visual the mixing of different energy in the fluids. This mixing is a whole thing in itself. Currently I don't plan to do anything in this area, but it is a very interesting area of the flow and combines a bunch of parameters that in free flow you can usually disregard, or at least they aren't important as otherwise. The lambda 2 ISO volume is a bit better at capturing the large vorticities than Q. I also faded the low turbulence kinetic energy values away. It shows the interaction between the large vortice coming off the back slope and the generally messy wake. It is apparent that the high turbulent air is being pulled into the rotation and it draws away the momentum quicker than otherwise. If we go back into the energy cascade plot, the small eddies dissipate energy more quickly than the large ones. Mixing the small ones with the large ones will make it far more efficient at removing energy from the large structures. Even though I wasn't going for a general fluids learning moment here, outside of learning transient simulations, this is definitely one. Finally, this case was developed from the OpenFOAM's Motorbike tutorial case. While starting, I ran this case, and I think it's worthwhile showing, as it illustrates transient flow with many different structures. This is a low quality case, so I could afford a large amount of runtime, so I'll just let this loop adding different conditions. There is an abundance of problematic flow here contributing to drag. We can see over the shoulder there is a great illustration of problematic flow captured and mapped to the surface by the wall shear stress values. Combined with the velocity slice through the middle of the domain, there is a better indication of how the velocity field and the wall shear stress are coupled.